Hi, Math 2504, Yoni here. Let me say a few words about Project One. You've done about 40% of the course, and now you have 3 projects left. That's 60% of the course. Projects are fun. They're also challenging, but they are fun. So Project One, individual work. The project has to do with computer algebra systems. You'll learn all about that from Paul Verbeek in the days to come. A good part of the project does not require computer algebra systems knowledge, but rather has to do with general computing. So you've got here the project page. You can read all about it. You can read the details, etc. Certainly recommend you do that. What we found in previous years was that students often took quite a while to get beyond task 1 and 2, especially task 2, which requires you to actually take the code that we give you and refactor it. Let me show you a little example of the code. So here I'm in the project repository, and I'm going to run Julia, and I'm going to activate. So I put it in package mode. I do the right square bracket, and I'm going to activate the project. And there are some packages already installed with this project. Let's just see the files again. One is a file called polyfactorization project. So if I do include polyfactorization project, what this does is it loads all of the source code of the project. Now, what do I mean by the source code of the project? Well, we already give you source code for this project, and what you do in this project is you modify the source code and you add to it. Okay, so the source code is available in this repo, and I see that the link is the link is not broken, but just the formatting here is bad. I'll improve that. And this is a repo. It's a similar repo to the repo that we had last year, only the tasks that we ask you to do are different. So you get a project, it already has some source files, and you should study these source files and just ask what happens in them. Go ahead and ask questions about that if needed. Okay, so we are here and we did this. So now we can, I think, do stuff like poly x or maybe x poly. Let's see. Yeah, okay. So here, this is a function that we provide in the project called x poly. It just creates a monomial x. And here we see this monomial printed. So if I ask what is the type of x, it is a polynomial. Okay. Well, what do we mean by that? Well, we can do something, for example, like x plus 2x, for example. And now we've got a new polynomial, 3x to the power 1. We can do x plus 2x to the power 10. And now we've got such a polynomial. We can do x plus 2x plus x squared, and now we've got a big polynomial. Okay, so the basic, and the type of this thing, the basic object in this project is polynomials. And what you do is you manipulate polynomials. So we already give you code that can do addition, multiplication, subtraction, and other more complex operations with polynomials. And your first task is actually an easy task. It's to change the way that this printing is done. It could have been done a bit nicer. For example, the polynomial x could have just been printed as x. We don't need 1 times x to the power 1, etc., etc. So the details are there. Now, the second task actually deals with refactoring the data structure used under the hood. So you'll need to read this and think about it. The way that we handle the polynomial in this point under the hood is as a dense polynomial. So even if we have a polynomial such as poly equals x plus x to the power 1000, okay, so under the hood, this polynomial actually keeps a list of all of the coefficients of the powers, x to the power 0, x to the power 1, x to the power 2, x to the power 3, up to x to the power 999, and x to the power 1000. So it is a dense representation. What we're asking you to do in this task is to change what's under the hood and make it a sparse representation. And we're asking you to do it using both a dictionary and a data structure called a linked list. We don't ask you to create your own linked list, but you can rather use a linked list available through datastructures.jl. So you'll need to read and think about what a linked list is a bit. The tutors can also help with that, and so can us lecturers and consultation hours. So after you do this, you can actually test that everything works. So let me show you what I mean by test. So if we go back to the project repo, let's just see what this thing is. Let me just do this here. Let's see the names of the files. We've got a file, we've got files called test. There's a file called run tests. So let me do include test run tests. And what this is doing is it is running the code under run test, which actually checks that the polynomials that we supply are doing Euclidean algorithm properly, doing the extended Euclidean algorithm properly, and just doing basic arithmetic properly as well. So if you go and you now modify what's under the hood in the polynomial, or make a similar polynomial type that is not exactly the same polynomial but should behave the same, you should also have tasks that do the same thing. Now, there's tests still running here, and that's why it still didn't print passed. It's still running, those tests. Okay, so if you want to see just here, let's look at the test code. See what run tests does is it uses these other files, integers, integers test and polynomial tests, etc. And each one of them supplies some function, prod polytest, prod derivative test polytest, etc. Okay, so it's running the test and it's passing. So now imagine that you're going to make one little change to this thing, and of course you'll do it under source control, so you can always go back, etc. Right? So you're going to do commits as you do changes, and as you do the changes, you still want to see that your tests pass. Okay, you don't want to make a change and then break the tests. Well, it's fine to make a change and break the tests, but then you want to find out why it's breaking and understand your mistake. Okay, and in some of the tasks, you also need to extend these tests. Okay, so what I suggest to do ASAP as a start is to download this repo, well, actually mirror it, just like we say, make a mirror of this repo for yourself, and actually start to examine the source code. And we define a struct polynomial, and it has a constructor. And for example, I'm not sure if you're across the new keyword, ask, investigate, etc. See what's going on. Dissect every little bit of the code, both in big picture and small picture, understand what's needed, dig into the project, and you can do a whole lot of that without knowing anything about computer algebra systems. Now, in parallel, you're going to learn about computer algebra systems, and that's going to be from Paul Verbeek, okay, an expert in the field. And what he's going to teach you will be needed for tasks effectively 5 and 6, okay? Maybe just a bit for task 4, but not a whole lot. Okay, so 4 is rather, is not mathematically deep. And in these tasks, you will implement the Chinese remainder theorem-based multiplication of polynomials, okay? And here you will do factorization mod P of polynomials. And now we already give algorithms for that, but you're going to improve them. So there's already source in the repo, but you will improve them, improve the algorithms. One last thing I should say is you take part in Paul's lectures. If you want a bit of background prior about algebra and number theory, especially if you didn't study those fields, then feel free to see these background videos here by Dr. Sam Hambleton. Not this ad, but these videos. Okay, the ad's cool too, but the videos. All right, so look at these videos, and they can kind of give you a refresher of numbers theory. But don't let that, my suggestion is, don't let that slow you down in getting into the coding aspect of the project. Okay, because there's a whole lot of coding to do, and I hope you enjoy it. Good luck. Bye-bye.